Okay, this is a video about projectiles. Let's have a look. Uh, uh, this kind of assumes that you know about SUVAT equations, and what we've got with projectiles is basically applying SUVAT equations in two dimensions. But there's sort of particular kind of problem because the upward direction and horizontal direction. The upward direction is well, it's constant acceleration, and the horizontal direction actually, generally speaking, exhibits no acceleration at all. So let's just have a look. Here we go. Here's an example. Somebody firing an arrow at a target. So we've got motion up and down. We kind of look at this from behind. We sort of see the arrow just kind of going up a bit and then coming down. Actually, in this case, it seems to be coming down back down to the same level as it started, but that isn't necessarily the case. In this one, the vertical displacement would be zero. Um, it's travelled up and down, it's travelled some distance vertically, but the actual displacement from start to finish would be about zero. Um, okay, and then we've got the horizontal as well. Now we're assuming there's no acceleration or deceleration, generally speaking, in these models. Um, and so what we're essentially looking at is a situation where we're applying this SUVAT equation to the vertical motion, um, okay, which incorporates the acceleration, and and then this to the horizontal, obviously excluding acceleration. In some problems, we are interested in this one as well, but really these pertain to situations where we're being asked to find the maximum height of a projectile. And the reason is that when we're thinking about vertical motion, then at the maximum height in the vertical sense, then the velocity is going to be zero. Um, okay, so now the key thing, I've got a worked example here, but it's really just an illustration of the fact that, again, normally in these problems, what given is we're given the speed of the projectile as it sets off. Sometimes we need to actually find that, but let's say in general, we're given the speed and the direction. So what we need to do is we need to resolve that into the two dimensions. So we need to know the horizontal component of that speed and the vertical. And in this case, as you can see, the horizontal, if the speed is 5 at an angle of 25, then the horizontal, which is denoted here by ux, could be ui, with ui and uj. That sort of connects us more to the sort of vector notation. But here ux is 5 cos 25, find the cosine of 25, which is that. And then in the vertical direction be 5 sine 25, which would be that. So as a vector, we can actually describe this vector as being 5 at an angle of 25 degrees, or we could do it in component form like this, those two bits that we've just worked out there and there as decimals. Okay. Now, one thing with all these problems is that well, we need to be clear about what our positive directions are. And conventionally, we kind of normally do up and right as being our positive directions. Um, if you didn't and you chose different directions, then it will all work out as long as you are consistent with expressing your velocity, your acceleration, and your and displacements um, with the necessary sign. Okay, so that's what we got. So if we let's have a look at this example here. A stunned person rides a bicycle off a straight ramp inclined 30 degrees to the horizontal at the end of a pier. The bicycle leaves the ramp with a speed of 14 meters per second, and the bicycle and some person are modeled as a single particle and land in the water at a horizontal distance of 28 meters from the end of the pier. So part A, calculate the time in seconds for which this particle are in the air above the water. So this is what we might term the time of travel. All right. So basically, this is the person's scooting off the end of this ramp. It's rather out of scale, really, but they're going off at 14 meters per second at 30 degrees. Okay, so we can see therefore, just going by what we said before about resolving the speed and direction, then the initial speed, which this is in the horizontal, we're looking in the horizontal direction here, that the initial speed is equal to the final, the initial speed in the horizontal direction equals the final, which is equal to 14 cos 30. Okay, 7 root 3, cos 30 being root 3 over 2. The displacement horizontally is 28 meters. We're given that. We don't know the time. That's basically what we're being asked, the time. So we're applying this Suvat equation here. This is like a simplified version of S equals ut plus half at squared, isn't it? With acceleration 0. And from that, we can work out, therefore, that t is equal to 4 over root through 2.31 seconds to 2 decimal places. Now, that is the time of flight. It's sort of a classic problem. This is work out the time of flight and then apply it to the displacement in the other direction. Usually you find, the displacement in the vertical or the horizontal, and you have to find the other one. That's a classic form of the problem. So here we go. Given that the end of the ramp was 50 centimeters, half a meter above the pier, find the height of the pier, giving your answer to the nearest tenth of a meter. So really what's happening is there's at the end of the ramp here, it's going down there. Okay, and we're going to find this displacement here, which is S, and I've given it subscript J. Right, okay, so, what we've got? Well, in this case, the initial velocity is 14 sine 30. Okay, we're going upwards, so we're going in, this is positive. We're going in a positive direction here. The displacement we don't know. It's going to turn out to be negative. Yeah, because our displacement is going to be downwards. The time we just worked out from over here, and the acceleration is minus g, the acceleration due to gravity, minus because obviously that is downwards and our frame of reference is upwards. So using this Suvat equation, then basically we just substitute all the bits in that we know. We know t, and so when we put all those in, we get this figure minus 9.967, etc. So I said it was going to be negative, didn't I? And that is because yes, we're actually coming down. So the height of the end of the ramp is going to be plus 9.9675, blah, blah, blah. And then when we take off the height of the ramp, we basically have got 9.5 meters if we're rounding that to 1 decimal place. Okay, so that's a very typical kind of thing. We're working out the time of travel and then we're applying it to the. Now, we'll see a problem in a moment, but where actually we are given the vertical displacement and we have to find the horizontal displacement. Now, if that's the case, what we've effectively got to do is we've got to use this in order to find the time of travel. So, because we know this one. We'll know that and so on. And in which case, we quite often end up with a quadratic equation, as we in t square in t. So that's a slightly different take on it. So let's just have a look, see what we got here. Okay, this is one from the Excel textbook. A stone is thrown from the top of a building, which is 8 meters tall. The stone is projected with speed 7 meters per second at an angle of 600 to the horizontal. Okay, so we can see how we're going to resolve that. The stone is modeled as a particle. Air resistance is ignored. Find the maximum height above the ground that the stone reaches. Right, okay, that's part A. Right, so here's a sketch. Here's the building. There's our 7 meters per second at an angle of 60. So we can resolve that into 7 sine 60 in the upwards direction and 7 cos 60 in a rightward direction. Incidentally, all these problems, you always see the particle going from left to right. If if you get a problem with that where it's illustrated with a diagram the other way, just going to have to be careful about which, what you do about your signs and which is your positive direction and so on. Okay, so the point here, going back to what I was saying before, is at the maximum height, then the vertical velocity, this is denoted by Vy here. I sometimes use Vj myself. Vertically, it's a bit of notation, actually quite nice. Just the upwards arrow to say that we're considering the vertical kind of equations. So the so this is basically saying that our displacement is well, it's just s. We only know it as s. We know u. The vertical is 0, as we've just said, and the acceleration is minus g. So when we plug all those into that equation, we've basically got an equation in S, which is that. And so that is the displacement above our starting point. Okay. So, but we're interested in the maximum height above the ground. So we've got to add the height of the building, which is 8. So that's going to give us a total of 9.875 or 9.88 to 3 significant figures, that's meters. Okay, so that is that one. Now it says find the time taken for the stone to hit the ground. Right. Okay, vertical displacement from start to end is minus 8 meters. So, all right. So now we're applying our displacement equation to this whole journey vertically. So we're looking at the vertical travel here. So yeah, minus 8. That is our initial velocity. Our initial velocity is upwards. That's positive. Acceleration is downwards. And the time is what we're trying to find out. So when we substitute those into there, we basically get this equation here. All right, and as I mentioned before, this is a quadratic in t. Right, so generally speaking, with these things, what we'll find is when we solve this quadratic, as has been done here, the t equals 2.0382 or t equals minus 0.8010. Well, we're going to reject this part of the solution because we're only thinking about positive time. Okay, so so that one goes, and we're just left with this one. And that is the solution. Now, we could go on from here, excuse me, to find the horizontal distance. Um, but it's not in this problem. Okay. Right, okay, so let's just wind down a little bit. So let's just have a look at the sort of the general situation that we're kind of looking at. It's a bit of a recap, really. So here we've got something being fired from this point here. Um, I mean, it doesn't have to go upwards. It could go like that. Um, but generally, we find these things are sort of being fired kind of upwards and outwards. Um, I've used big U there because to save confusion with the Suvat equations. Um, yeah, so that's what we've got. Acceleration obviously is minus g. We're using that equation most typically, where our initial velocity is this. All right, and then when we're thinking about the horizontal, well, again, generally speaking, acceleration equals zero. It's possible we could actually have, have something slightly different. Um, but I think you'd be unlikely to get a question like that. But if you did, you can apply these same principles. We just obviously would use, um, a form of the equation like that rather than like that. So let's say no acceleration. Okay, so those are our two dimensions. Now, note what is common between these two is, first of all, we've got the same value of u. Um, it's the same speed. We're just resolving it in two directions. I mean, it might come to us already resolved, but essentially it's the same initial velocity being fired up at this angle, and it's the same t. So we've got two equations in two unknowns. Familiar? Yeah, of course, simultaneous equations. Now, we're not necessarily solving them in the same way that we're kind of used to solving, but them not necessarily, but we might be. We might be. There are problems that you may well get in your examination where both U and T are unknown. And if, for instance, we were given the horizontal distance displacement and the vertical displacement, we'd be able to put these two equations together and solve for both for u and for t. So that is the general idea of these problems. Sometimes they're expressed in vector form. Um, so um, sometimes your vector, your initial velocity is given to you in IJ form. But really, from that, you can just pick out the information that you need. Right, let's just have a look at. There's loads of examples of these. Let's just have a look at another one. A projectile is launched at 8 meters per second from the origin, at an angle of 60 degrees to the horizontal. Find the length of time for which the particle is at least 2 meters above its launch point. Right. Uh, so, so part A. I've called this part A. I've added a bonus question on here myself. Part A, vertically then, we were using this equation here. I've used subscripts Sj, and horizontally we're using that with subscript I. So vertically, um, what I've done here is, and we could solve this as an inequality. I actually found it easier in this case just to solve it as an equality. Find the points in time where the height is 2 meters above the starting point, and then deduce the answer from that. So S equals ut plus a half a t squared. All right, so when we work all that out, we get a quadratic in t squared, and we solve that for for this. T equals 1.01 and 0.404, and therefore the time we can see from that obviously at this time it actually goes above, and this is where it comes back down again. Okay, so that between there and there, essentially, on the diagram. So that gives us our answer. And then how far does the projectile travel? Well, okay, with s kind of s equals ut plus half at squared. Um, so so this is basically we're looking at the total time here as we're resolving again, but for when the displacement is zero, and the displacement is zero is when it's come back down to the ground. So between here and here, the displacement is equal to zero. So that's why we can form that equation, which becomes that equation. And when we solve for that, then obviously one solution is t equals zero. Yeah, and the other one is when form root 3 equals 4.9t, which is going to give us that. So the time of travel is 1.41 seconds for it to go from there to there. The uh, the the displacement horizontally is going to be v times t. Well, v is 8 cos 60. Cos 60 being a half means that it's actually 4 in that direction. So that is our horizontal velocity times the time, giving us 5.64 meters. Okay. So again, it's the same theme really. Very often we're using the vertical to find the time of travel, and then from that we'll find the horizontal distance. But these problems come in sort of variations of the same theme. Okay, so now as lots of other examples, we'll put those in a separate video, and I hope that has been useful. So thanks for watching.